if you want to simulate nature, you better make it quantum mechanical, or otherwise, you can't simulate nature.
All right. Welcome, everybody, to the Sasberry AI podcast. And today, for our pre-Valentine podcast, we have Himank Pande. And he joins me here from also in the same town as I am in Maple Ridge, British Columbia. But I'll let him introduce himself, because today we're going to talk about something very interesting. We're going to talk about quantum computing with someone who really knows about quantum computing, with extensive experience with it. So, hi, Mac, take it away.
All right, thanks, Steve. Thanks for first off inviting me to this conversation. I don't know if I am that prolific with the whole quantum technology, but yeah, I'll try to do my best. So just a quick introduction. I've spent almost the last 15 years, starting from Cisco Systems to Amazon Bracket, learning the hardest part of innovation, which is not the science, but it's actually being able to like operationally refactor and make science useful, right? So back in Cisco, I started off as a voice over IP engineer, and of course, there was a lot of science. There were digital signal processors within these IP phones, a ton of science and IP inside it. Video conferencing devices, and even the systems that actually manage these. So that's where I started, and I've always tried to understand patterns and then apply in my next job. So from Cisco, I moved on to NIH, National Institutes of Health. And from National Institutes of Health, I came to AWS, where I started off as a TPM with the enterprise engineering team. I was managing Slack and Chime and video conferencing, their emergency systems. And from there, I just stumbled upon into quantum, and I was like, hey, what's this got to do with what I'm doing today? That's where I talked about earlier. I talked about like recognizing patterns, learning from those patterns, and then like finding out what are the best mechanisms to grow from those patterns. So yeah, that's like a brief introduction of mine, and yeah.
Great, thank you. So, so since this is a pre-Valentine podcast, we're going to talk about, but we're going to talk about qubits instead of cupids. So yes, that joke. I apologize. I had to try it. So, all right. So with that, can you, in plain English, try to explain to me the difference between bits and qubits?
Yeah, sure. So again, just to kind of give you a backdrop, quantum is not magic, like you just mentioned. There's bits, there's qubits. I'll come to that in a bit, but I just want to know it's not new magic. It's just new math and new hardware. Like you've always had some math being done on GPUs, some math being done on TPUs, on CPUs, right? There's some new math on a new hardware called QPU, or quantum processing unit. So the basic difference lies, and I'll give an analogy. I think it's the best to understand that ways. Think of a bit as a light bulb or a light switch, which is either on or off, and a qubit is basically a dimmer switch in a room, which is full of these mirrors, right? And the reason why I want this switch to be in this bulb light switch to be in a room is with the mirrors is because that builds upon the two specific properties of a qubit, or multiple qubits, which is entanglement and superposition. So at the very base of it, and because personally I am also, I'll give another analogy, because I am from a musical background as well. So a classical bit is like playing a single note on a guitar, versus like qubits would be, the superposition of qubits would be like playing a chord, wherein multiple tones or multiple states are present at the same time. So like those two analogies.
So that's actually a really good explanation of what superposition is. I do like the analogy itself. So, but So what makes this so important? Dealing with bits versus qubits, like in terms of practical usage, why would that make such a big impact?
So I want to quote, and thanks for that question. I want to quote Richard Feynman, who was a pioneer in this field, who actually said that nature is not classical. He said that if you want to simulate nature, you better make it quantum mechanical, or otherwise, you can't simulate nature, right? So the reason why this matters today is purely because of the scale, right? Think of this as like as a metric that in order to simulate 300 entangled qubits together, you would probably need bits than there are, like, more than there are atoms in this whole universe, right? So it's like one of the major reasons why this matters today. We want to get better with the compute that we have, which is a bottleneck in a lot of our workloads today, especially around AI. But one specific metric I want to bring up is that the fact that in classical computing, in order to double your power, typical Moore's law, you have to double your hardware. But in quantum, it's exponential. It's actually 2 to the power n. So it's basically, in order to to simulate, like I just mentioned, like 300 entangled qubits, classically, you would actually need more bits than there are atoms in this universe. So that itself is the scale of why this matters today, because future technologies would either be dependent or would be directly engaged with quantum at some point.
That's awesome. So there's another concept that is often brought up when discussing quantum computing, and that's entanglement. So help me understand what entanglement is.
Okay, so Einstein actually called this spooky action at a distance, and this is also like one of my. I was watching this nature video wherein I really got into spooky action at a distance, and there was this experiment which was happening, I think in Germany or in Netherlands, I forgot, but yeah, this was this experiment wherein they were trying to come up with, they were trying to measure from an observatory, or I think two separate observatories, the calculation of entanglement. They were trying to find out, what happens. Does entanglement even work? And they actually found it that it did work. So just to kind of like a one-liner, just going back to my analogy of the light switch. So bit was a light switch on or off. A qubit was I could dim it, basically have multiple states of the light switch. And entanglement, remember I told about this light bulb inside a room full of mirrors. So think of this as, I'm trying to dim that light switch. The other light switches on the mirrors are instantly reacting. So think of this as, if a particle, the correlation between like two particles is so tight that the distance doesn't matter. If you flip one entangled qubit, in Ahmedabad, Gujarat, it would actually flip its twin here in Vancouver, and they will always match. So that's essentially entanglement.
That's pretty neat. So this is actually a good opportunity to kind of jump into why how it matters when it comes to AI. And in our previous conversations, we talked about quantum computing and on running alongside APU, CPUs, TPUs, GPUs, and how that will work. And that kind of segues into hybrid workflows. Help me understand how quantum and AI intersect in this from a computational sense. So,
Got it. So before we get into the intersection, I want to really talk about this virtuous cycle. It's basically, we are using AI to constantly design and stabilize the quantum hardware, because quantum hardware is noisy. And you can't expect quantum hardware to have 5 nines of availability, and you can't avoid like certain like specific moments where physicists would come in and make sure that the quantum hardware is working as expected. You can't expect that 5-9 availability with quantum hardware today. In order to make that better, in order to remove noise, we basically use AI. And that's where I talk about the virtuous cycle, wherein I say that, we use AI to design and stabilize our quantum hardware, and not just the quantum hardware, but also the software and the security around it. And then we also, and in turn, we are using that quantum hardware to solve the math, which is actually making AI too expensive. And I'll come to that in a bit. So basically, it's a closed loop. It's a virtuous cycle. And I think I think IonQ's CEO actually said this, that they are currently using AI to build better quantum computers, so that quantum computers can eventually build better AI. So that's like, the leaders acknowledge this as of today, and there is no stopping of AI and quantum intersecting. Now, having said that, you know, traditional AI, it's basically being used today to fix a lot of inherent noise. So I'll give you a recent example from Google. So, for example, they used, I think, reinforcement learning. Basically, they used that as an agent to improve something which is called a surface code. So surface code is kind of a quantum error correction, which is essentially a mechanism which is used to, improve errors or noise inside quantum computers. And they were able to prove this, that by using this RL agent, or a reinforcement learning agent, they can improve that metric. I think they achieved almost 3.5 times, improvement against the environmental drift. So that's like one metric, and proof that, this AI can help build quantum better.
Wow, that's actually didn't even think about it from that point of view, and this is very much a symbiotic relationship, isn't it? So,
That is true.
So let's jump into, I mentioned this earlier, but help me understand, like, what's the difference between something like a GPU, TPU, NPU versus a quantum chip? Fundamentally, an architectural level is very, very different, but how is it different, like hardware wise, and how is it different from the applications you're building for usage in this in the quantum world?
Right. So I think like it's basically about capacity and who does what, right? But when it comes to quantum computers, I mean, I want to put this in record that, as AI workloads are scaling, and the memory is hitting a wall, we are moving to this idea of a physical AI, where quantum will be able to do some parts of that hybrid workflow that you just mentioned. So there will be some part of things that will be done in classical, and then the other part of things that will be done, in quantum. And this is also where, I just wanted to make sure that I also mentioned that, AI for quantum I mentioned, and then quantum for AI is where, these quantum computers can actually solve problems for AI using like large quantitative models. I think this is the active work being done, and even quantum AI, which was something, it was a term which was coined at AWS when we said that, hey, how can quantum help AI? So just going back to that idea of the where these chips fit in, and where exactly does the quantum hardware or quantum processing unit even fits in, right? So think of CPU as, like a general purpose control plane, right? It's the project manager, kind of an orchestration layer, right? Probably 1 to 5 teraflops, wherein which is great for orchestration, but not great for like, it's not a power horse like a GPU, which think of it as, just going back to my music analogy, the throughput orchestra, right? You've got, it's a parallel workhorse. You've got 80 to 300 teraflops, great for training, And then comes the savants, right? The NPUs and the TPUs, which are very specific. For example, if we talk about the TPU, it's specific for matrix multiplication, and then NPU is specifically for like on-device inference. So with the relatively less teraflops. But the crux of the point that I'm trying to make here is that in the future we won't have a war. It would all be together, right? This will be like a symphony orchestra, which will be playing all together: CPU, GPUs, TPUs, maybe NPUs if Elon Musk is able to remove phones from our from our hands and put everything on the edge, and then these QPUs would actually sit right in that data center, and will be improving the efficiency, the cost performance of, for example, the large language models using quantum AI, or the work which is being done just at the AI level.
So, so one of the things about AI, the pretty much the heaviest load really is when it comes to machine learning and training, right?
Mhm.
Can 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 quantum computing help this specific area? Because really, that's in order for us to really progress and train and build these large language models, and make them more progressive, essentially,
Right,
in greater leaps and bounds. That heavy lifting has to be done by kind of a different methodology, right? So
right,
how does quantum computing help that aspect of it?
right. So as I just mentioned, and just going back to the whole intersection between AI and quantum, talk that I was just giving, I did miss talking about the how quantum can help AIs, and that's where I want to make this point about uh, you know the basic difference between classical and quantum is about how they work. So classical memory is linear, like n bits, versus the quantum memory is exponential. It's like 2 raised to the power of n states that can actually happen, right? So for example, if I take the example of like GPT, they require massive state space, right, to understand the relationship between the data. uh, Typical LLM, right? So quantum AI, and the reason why I want to focus on this phrase is because I come from Amazon, as my previous job. Quantum AI is actually is a term which is available on AWS. You can Google it. Its aim is to replace the underlying AI infrastructure with quantum computing resources, right? They want to replace it, but that won't happen today. It's a theoretical concept, at least for the most cases. But there are like improvements being made, research being done almost every day, every week, to kind of go to that point. So it will be a classical and quantum, classical plus quantum, or a hybrid classical or a hybrid quantum mechanism. And the benefit would actually be around like reducing AI training costs, because there's an energy wall, there's a model bloat. Those are like two big problems which the AI needs to solve. And just because of the fact that there's this massive state space which a quantum memory can support, so instead of having like so many processors to train an AI model, you would probably have like some sort of a balance between GPUs, CPUs, and QPUs, or maybe TPUs, probably working to to train these models. So that's one. And then quantum AI can also improve prediction accuracy, right? They can perform some complex probabilistic simulations and optimizations. Mind you, this is all at scale. But the reason why I say this is theoretical is right now because we don't have quantum computers, one, operationally stable, and two, they are available for like specific use cases. And slowly and steadily, there's advanced scientific research and new algorithms which are being developed specifically for hybrid quantum classical use cases, which can actually make quantum AI a reality in the next few years.
Speaking of next few years, let's talk about short term and midterm, right? Where is quantum computing going within the next 2 years, and what is it looking like beyond that? Because we've had quantum talked about a lot over the last few years, but where are we? What is the reality, and when do we see it actually in actual production, right? So can you tell us about that?
So there are two ways to answer this question. One is what is happening today, and what the roadmaps are saying, right? Because mind you, the roadmaps can often be more hype versus reality, right? And quantum companies might when I say quantum computing companies, I mean the quantum hardware providers, the big ones, uh, and even the ones which are coming, they might come and tell us that, hey, quantum supremacy is here, and we are able to simulate. I think we are able to simulate teleportation and actually make teleportation, and it would be news all across. So that's not the case today. I mean, pretty sure there's good reason why people say that, because based on the factual aspects, right? Uh, we want to make sure that within the next 12 to 24 months, we are looking at like real cases or real use cases. Like, one of the things that I see is quantum and HPC is kind of getting really close together. So the reason why I say that is because high performance computing and quantum kind of go hand in hand, and it has been acknowledged by the industry. There are government hubs or quantum hubs which are coming across the world, where research communities are basically collecting together into this single hub, and then they're improving their overall research quality and their research results, etc. And then these quantum hardware providers are helping, they're providing quantum hardware to these hubs. So from a technical standpoint, quantum and HPC are going to get closer in the next 12 to 24 years. Then I think NVIDIA, that's so this is on the quantum side, right? Wherein we just have like some quantum processors sitting in a data center along with other GPUs and TPUs, etc. But there's also this aspect of distributed quantum networking, which people are talking about. I am a little, skeptical, but because there are a lot of major improvements that have been made, just in the way you can network two quantum computers together, by big network companies and even companies like NVIDIA. They want to make this AI factory wherein they've got multimodal quantum computers sitting inside a data center, and alongside you've got an H100 or a H200, the power workhorse. So that's the direction to which at least in the next 12 to 24 months things are going. Apart from that, I think one of the important things that the industry is working is towards gate fidelity, right? So right now, I believe it was IonQ that hit like 99, like 4 nines of 2 qubit gate fidelity. And I think the other industry, will also catch up to that metric. But apart from fidelity, we also want to make sure that the number of qubits, right now, I think we probably have 1,000 qubits in a couple of quantum computers, like I think Atom Computing, and I believe one by IBM. So that number of qubits need to evolve, right, in the next 12 to 24 months. And there are aggressive roadmaps from these quantum manufacturers, which are taking us there. But in the next 12 to 24 months, I think quantum and HPC are going to be much more closer together.
Exciting. I'm really looking forward to it just because of the incredible breakthroughs that we could gain. And again, we're not talking like small increment improvements. Once quantum computing comes into reality, we're talking about massive leaps, which brings me to the last and final discussion here, and that obviously in the world we live right now, there are a lot of geopolitical issues, should we say.
Yeah.
So we do need to talk about who's in the lead when it comes to quantum research, and who's closest to actually getting it into from the lab to reality, right? So what would you say?
Yeah, that's a great question. But the way I look at it is we are moving together at this, and I think I read this great article in LinkedIn. I believe it was somebody who said that it's not about the qubits that we are scaling. It's not about how many quantum computers we have created. It's not about how many countries are putting billions of dollars or who's in the lead. I think the question is, do we have an understanding, between all of us that we are moving towards a common cause? I think that's something which really struck me, and I was like, this makes sense. The reason why I say that is, you know, there is a lot of different companies creating IP. Their own intellectual property. They're making their own quantum computer, which is great. Wrapping around APIs, which is awesome. The problem is that, and this is what I see, having worked in the industry for almost 3 years, that we need to become more closer intertwined together. We need to have like standards, some kind of standards, which can make some, like a quantum computer talk to another quantum computer, for example. And I believe quantum networking is the answer. But I think we need to develop an understanding, of where we are taking this entire technology together. I think that's really critical. So that's the first thing. If we just talk about the the where the market is going, I think the AI industry will be the ones who would actually be first adopters of quantum. And the reason why I say that is purely because of the fact that, the immediate use cases, as soon as HPC gets closed, I think the next, the next segue would actually be AI. And of course, we want to make sure that people are trained and quantum literate before that happens. So yeah, it's more about like working together versus letting somebody lead towards quantum supremacy, or claim, for that matter, quantum supremacy.
Yeah, like they say, the rising tide floats all boats, and
Right.
and I hope that that is truly the case. I mean, this is such a massive undertaking, and I think it does require all major players, all major countries coming together to achieve this very, very important goal. So, well, Himank, I'm going to draw us to a close here, but I really do appreciate you joining me today, and it helped me scratch that intellectual itch that I had regarding this, and then I hope to chat with you more about this in the future. So, thank you so much, and have a great day.
Awesome. Thanks, Steve. You too. Have a great one.